Okay, so Assalamu alaikum and good afternoon, good morning if there is somebody from a different region. So welcome everybody for this seminar, the CSM International Webinar on Construction Material in Greenation Era. The series number 1, Challenges in Concrete Technology, which is organized by Concrete Society of Malaysia and co-organized by University Technology Mara Shah Alam, UITM, University Tun Hussein on Malaysia, American Concrete Institute Malaysia chapter, and Narotama University. So I'm inviting now Associate Professor Dr. Haziman for the opening remarks. Associate Professor Dr. Haziman, he is the President of Concrete Society of Malaysia, and he is a Deputy Dean for Academic and International Faculty of Civil Engineering and Built Environment, University Tun Hussein on Malaysia. So the floor is yours, Prof.
Okay, thank you, Dr. Wesam. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to everybody. First, I welcome everyone to this joint international program, Concrete Society of Malaysia or CSM International Webinar on construction materials in Greenation Era, which organized by Concrete Society Malaysia and organized by University Tun Hussein on Malaysia, University Teknologi Mara Shah Alam, Universitas Narotama Surabaya, American Concrete Institute Malaysia chapter. Okay, this is the first series of our periodically webinar online session. So in future we will have another session, maybe in September or maybe in October, inshallah. So firstly, I want to thank to the all speakers, Professor Dr. Hamidah from CSM or UITM Shah Alam, University of Dimara, Dr. Jacqueline from American Institute, okay, American Concrete Institute Malaysia chapter, Professor Dr. Amir from India, and Professor Dr. Lim from CTU Hong Kong. Okay, this is a platform which aims to share the knowledge on sustainable construction, especially on green construction material. Okay, green construction materials, and build up networking among us, especially among engineers and also practitioners who are so passionate about contributing to the promotion of sustainable practice. A sustainable lifestyle which balances the economy development needs with the environmental protection, taking into account the social dimension. The goal of sustainable development is to increase the quality of life for all people without increasing environmental degradation and without compromising the resource needs to resource need of future generation. We can do this by shifting our consumption patterns toward goods that use less energy, water, and other resources, and by wasting less food. Okay. In this year of transformation, we hope to see great advance on sustainable development and climate change that make this remarkable program a start of a positive change movement for more sustainable and healthy planet. Let us think about the environmental consequence of the choice we make. Last but not least, I wish you a successful program which will have a positive global impact for the betterment of the humanity. Thank you. That's all. Thank you, Dr. Wesam. Dr. Wesam, I cannot hear you. Please unmute.
Okay. Thank you, Prof, for the opening remarks. And now I hand the session over to Dr. Ihsan, the Vice Rector of Narotama University, to moderate the first session.
Okay, terima kasih. Thank you very much, Professor Haziman, as President CSM and Professor Wezam. Session is keynote Professor Dr. Hamidah Muhammad Saman from UITM, Malaysia. She also Honorary Secretary, Congress Society of Malaysia, CSM, and a member ACI KL chapter, also EXCO member Confederation of Scientific and Technological Association in Malaysia, COSTEM, and graduate member of IEM, Institute of Engineers, Malaysia. So Professor Hamidah, are you ready? So this time is for yours as keynote speaker, Professor. Can unmute, Professor? Okay.
Okay. Okay. Okay, good afternoon, everybody. And thank you, Professor Ihwan, to share. Boleh?
Coba tak lagi ya.
Sebentar. Good afternoon, ladies and gentlemen. Today, I would like to share small fractions of innovative materials and methods that have been made worldwide that have opened new doors for improvement in construction industry, particularly in concrete construction. I cannot share because somebody disabled my screen sharing. Dr. Wesam, can you help me?
Yes, Prof.
Dr. Wesam, because I'm disabled to share the screen.
Yeah, Dr. Ihsan will do that because they need to assign. Yes.
Okay, still disabled. Who's disabled attendee screen sharing? Why?
Yeah, because normally for the speakers, they need to assign as a co-host. Then they can share.
Pak Ihsan, Prof Hamidah tak bisa untuk show slide. Ada somebody yang apa? Okay.
Kan co-host Pak Ihsan. Sudah.
Okay.
Bisa.
Sudah,
Prof Hamidah.
Okay.
Co-host.
Ya. Okay. Now okay.
Okay.
Okay, everybody see my slide?
Ya, clear, Prof.
Okay.
Clear.
Clear, Okay. So I would like to share small fractions of innovative materials and methods that have been made worldwide that have opened new doors for improvement in construction industry, particularly in concrete construction in the Greenation era. So good afternoon, ladies and gentlemen, everybody. Smart materials are defined as that have one or more properties that can be significantly changed in a controlled manner by external stimuli such as stress, temperature, moisture, pH, electric or magnetic fields, and smart construction materials, which are also known as intelligent, active or adaptive materials. One of the smart materials is shape memory alloy, or the acronym is SMA. SMA have two unique characteristic. One is a shape memory effect, and another is super elasticity, or known as pseudo elasticity. And SMAs are alloys that can return to their original form, shape or size when subjected to thermomechanical or magnetic variations. The SMA have two stable phases. One is a high temperature and another one is a low temperature. The high is called austenite, while the low one is called martensite. A phase transformation which occurs between these two phases upon heating or cooling is the basis for the unique properties of the SMA. The most common SMA are nickel, titanium, copper, zinc, aluminium, and copper, nickel, aluminium. And therefore, SMAs are still considered as expensive materials. SMA find their application in civil engineering, specifically for seismic protection. To date, SMAs have been applied in concrete structures to enhance shear resistance and reduce crack width for bridge girder. Nickel titanium shaped memory alloy wires have been used to repair and strengthen heritage structures. SMA is also suitable for bridge restrainer that prevent excessive movement in bridge supports during a severe earthquake. Another application of SMA in construction is as base isolator. The SMA isolator usually provides energy dissipation and restoration after unloading. The isolators are installed between superstructure and the ground to assemble uncoupled system. Therefore, the damage of the superstructure is minimized. SMA also can be embedded in concrete structures to reduce the permanent deformation. Ladies and gentlemen, concrete has gone through evolution and revolution since the establishment of ordinary Portland cement in 19th century. In 1980s, use of blended cement is becoming interest of numerous researchers, and the studies on behavior of blended cement utilizing waste byproduct ash and are aggressive, and at the same time self-compacting concrete was introduced. And late 1990s, ultra high performance concrete, or known as reactive powder concrete or RPC, was invented by a group of researchers from France. Recently, category of self-sensor, self-cleaning by using nano-sized particles and translucent concrete under the term of smart concrete have been topics of discussion. Example of self-sensoring in ready-mix concrete is real-time concrete strength monitoring. Wireless sensors are installed in the formwork to obtain and share real-time concrete strength. And concrete incorporating with carbon fibers, carbon nanotubes also can be used to sense the strain, stress, crack, or damage by itself. The sensing ability of smart concrete are based on the electrical charge of resistance. Carbon fiber has been proved to be one of the most effective way to improve electrical conductivity. Therefore, is embedded in hydrated cement paste. Carbon fiber in concrete can act as a self-sensing sensors electrical resistance change. Self-sensing concrete also can be used to monitor traffic flow and reduce congestion, and these can be done by integrating a signal from self-sensing concrete with intelligent transport system. In cold countries, self-sensor concrete can melt snow, alternative to using de-icing salts, which create many issues mainly on corrosion of steel reinforcement. And the concrete is integrated with a resistive carbon nanofiber, paper, and heat will transfer to the surface through conductive concrete. Nanotitania can disintegrate organic pollutants into harmless CO2 and water. in the presence of light, make buildings stay cleaner and more beautiful. Nanotitania act as a photocatalyst for coatings that can preserve paint color for years and produces self-clean surfaces. Meanwhile, Prof. Henk Jonkers and Prof. Eric Scalingen from Delft University, Netherlands, in early 2000 had noticed that bacterial activities tend to self-heal by generating calcium or calcite precipitation, and their bioconcrete would have encapsulated bacterial spores that would be activated when cracking takes place. It is a special type of concrete. Bioconcrete and self-healing concrete is a special type of concrete that formulated to increase durability and its lifespan by continuous healing action. The bacterial species produce urease, which catalyzes urea to produce CO2 and ammonia, resulting in increase of pH in the surrounding where ions of calcium and CO3 precipitates as calcium carbonate or called as calcite. Bioconcrete leads to sustainability because microorganisms can be regrown, and it is a new way to design durable concrete structures. The beauty about bacteria is it will become dormant in spore when water and food is depleting. But when the bacteria receive food and water, it will revive, become active even after millions of years in dormant state. The introduction of nutrients and with the ability of oxygen, bacteria can precipitate calcium carbonate to fill the micro cracks. These techniques are also called microbiologically induced calcium carbonate precipitation or MICP. Bacteria that used for self-healing must be easily obtained, safe, calcite forming and spore forming bacteria which are also resistant to pH and temperature. The calcite formed from bacteria will fill up the voids in between the aggregates. This is the illustration that can be made when the calcite is formed in concrete. Ingress of water through cracks activates the bacteria, converting nutrients into minerals, locally clogging the crack to regain water tightness. Another method of self-healing is by using polymer catalysts. When cracks occur, the microcapsules containing polymer healing agent break and release the healing agent. The healing agent is in contact with catalysts that also embed in the materials, causes polymerization and fill up the cracks. Research has been conducted in the Faculty of Civil Engineering, University Teknik Umara, on self-healing concrete using Geobacillus stereothermophilus encapsulated in alginate gel. The encapsulated bacteria was mixed in concrete and then artificial cracks were introduced. It was observed that the cracks will fill up in 60 days. The study showed that encapsulated bacteria can heal the maximum crack width of 0.97 millimeter as compared to direct incorporation of bacteria. Smaller crack width only can be filled up. Meanwhile, nanoconcrete is defined as a concrete made by filling the pores in traditional concrete using nanoparticles of size less than 500 nanometers. The nanoparticles will provide special performance. Carbon nanotube possess superior of mechanical properties. Besides its very low density, making carbon nanotube one of popular nanomaterials selected to be incorporated in concrete. Nanomaterials are categorized into two, which are graphene and nanoparticulates, and which are carbon nanotubes, or in short CNT, and carbon nanofibers, or in short C and F. Meanwhile, nanoparticulate materials include titanium, silica, calcite, and clay. Graphene is a monolayer of carbon atoms packed into a honeycomb lattice. Graphene layers can be wrapped into perfect cylinders. Carbon nanotubes, or in short CNTs, have diameter 1 to 2 nanometers and length up to 18 centimeter. It has extraordinary strength, excellent electrical and thermal properties, making CNTs the best of materials as compared to carbon steel. CNTs fit many applications in infrastructure. CNTs have strength hundreds of times of that of steel, can be employed as rope in suspension bridges. Some scientists are even working on a space elevator that use a CNT rope to take us all the way up into space. CNTs have been used to fill up pores in concrete that range from nanometer to millimeter size in pores, resulting in more durable concrete. Owing to greater strength and lesser density of CNTs, it can offer an excellent replacement to conventional steel as cable-stayed bridges. Carbon nanofibers, or CNFs, are fibers with diameter in the range of 10 to 80 nanometers. CNFs are cylindrical nanostructures with graphene layers arranged as stacked cones, cups, or plates, or even as coil or ropes. Besides, can be a photocatalyst as self-cleaning agent. As mentioned earlier, nanotitania, when exposed to UV light, will create hydroxyl radicals and superoxide ions, which are very strong disinfectants as a cleaning agent. Nanosilica, because of its cheaper cost, is the most commonly used. Silica is found in nature as sand. Nanosilica particles range from 10 to 20 nanometers. Nanosilica, when incorporated in concrete, would fill the pores at a nanoscale, resulting in increase in compressive strength of the concrete and improve the resistance towards segregation. While calcite is a common carbonate mineral, the second most abundant after silicates, size of the nanocalcite particle exists in the range between 60 to 150 nanometers. Nanocalcite is very important filler material like nanosilica and can be used in sealants and adhesive to improve stiffness, improve resistance, and weatherability of the resulted composite. Owing to its glassy texture, calcite also impart glazing to paints. While nanoclay is made up of platelets with thickness of 1 nanometer and length and width in range of 200 to 400 nanometers. Each granule of nanoclay contains hundreds of layers. 1 gram of nanoclay contains over 1 million individual platelets. Nanoclay is added to concrete as a replacement of cement material. It was found that tensile strength of concrete increased by 50% if 8% cement is replaced by nanoclay. Nanoclay is also used as rheological modifier in paints and increased flowability and plasticity if added into concrete mix. Research works have been done in the Faculty of Civil Engineering, University Technology Mara, UITM, on utilization of nano clay in producing ultra high performance concrete or UHPC, and series of trial mixes were experimented to determine the optimum formulation with high workability UHPC, incorporating nano metaclay and nano metakaolin. It is an objective of the study to establish ultra high performance concrete made of nanometaclay or nanometacolin with water curing but can achieve similar strength as those of UHPC made of other materials cured in elevated condition. The function of nanometaclay or nanometacolin is obviously to fill up pores in nano size in concrete. The results show that nanometaclay has flaky and granular morphology. It shows that 1% nanometacolin is enough to boost the compressive and flexural strength of maximum level of the UHPC prepared. Interestingly, it is noted that the compressive strength achieved is equal to those made of higher cement content and cured under heat treatment when nanometaclay or metakaolin is included in UHPC. Similarly, flexural strength obtained is equal or higher despite of lower cement content used. It is confirmed that inclusion of 1% nanometacolin and 1% nanometaclay enhanced the compressive and flexural strength, and both strengths were achievable from UHPC specimens cured in water. Another smart materials is translucent concrete. Is another example of smart concrete. It is also called transparent or light transmitting concrete. It is achieved by replacing aggregate with transparent alternate materials. For example, clear resins and other type of resin. Translucent concrete was originally developed in 2001 by a Hungarian architect. Transparent concrete is manufactured by using combination of fiber optics and fine aggregate. These fibers are blended into the concrete like any other aggregates. These optical fibers can transmit light from natural and artificial sources into spaces enclosed by the translucent concrete panel. The main reason for using optical fiber in concrete is that it can transmit light even an incident angle greater than 60 degrees. Optical fibers in concrete act like slits which pass the light throughout the concrete. Translucent concrete offer many advantages such as good aesthetical view to building, save energy costs if uses sunlight as light sources instead of electrical energy, and can be used in cold weather countries to transmit heat with sunlight. Artificial intelligence or AI assists humans and not replacing them. AI or artificial intelligence uses power of machines to model natural intelligence of human. For example, drone provide easy access to monitor construction site, workers at large and difficult areas or complex areas. A drone can gather images, aerial data, and mapping information, and drone is used to capture 3D modeling for building information modeling or BIM. While BIM creates a shareable digital description of every aspect of the structure which all necessary stakeholders can update. BIM offers solutions regards to cost estimation, design workflow, life cycle management, streamline information, documentation, and also maintenance. Few research in relation to drone and BIM are ongoing in the Faculty of Civil Engineering. We have a group of researchers conducting research on BIM and drone technology, and few papers already submitted and published in the journal, High Impact Journal. So, ladies and gentlemen, that's all my presentation. Thank you very much, and I hope you can benefit some of you of the information. Thank you.
Okay, thank you very much, Professor Hamida, for great presentation. So, Professor Haziman,
Cannot hear, Prof. Iwan. Can you speak louder?
We open for QA or for next keynote, Prof. Haziman and Professor.
Okay, we proceed for the second speaker first, Dr. Ehsan. And after the all speaker finish their presentation, so we can open for Q&A.
So we start to next speaker keynote.
Yes, we start. We proceed for the next speaker. Okay, we start with the next speaker. Prof. Dr. Zach Lim.
Professor Zach Lim.
Dr. Zach Lim, yeah.
You can unmute, Prof. Zach Lim.
All right. Yes. Yeah. Done.
Okay, clear.
Okay. Yes. Good afternoon, everybody. Okay. Shall I proceed?
Yes, you can start, Dr. Zach.
Okay. All right. Yes. Good afternoon, ladies and gentlemen. I say thank you very much, Prof. Hamida, for giving us a very eye-opening thing. Even I learned a lot about nanomaterials. But I'm going to talk more because I'm a concrete floor specialist. So my talk will be more related to the concrete floors, all right? And I know today there's a lot of lecturers and students listen to this talk. So I hope to share some of my experience and knowledge, especially on concrete floor cracks, all right? Okay, so today my topic is what are the challenges of concrete at the job site, right? So, okay, so I can think of 5 challenges at the moment, all right? So you know very well about this concrete. Most important is the mixed design. So I always say that one concrete mixed design does not fit all, isn't it? For example, when you're doing a highway, you need different type of concrete, you need a structure, you need different type of concrete. Like, for example, like us doing concrete floors, all right? We need to have the concrete to kind of set at a longer period, all right? So like 3 to 5 hours, things like that. So that's the reason why mixed design is very, very important. Okay, so let's come to the challenges, all right? The first one is concrete quality and the slump consistency. The second challenges is supply concrete with good workability, right? And the third one is using supplementary cementitious material. I'll talk about some of the advantage and disadvantage on that. Okay, and the fast set, all right? Today, everybody wants their job to be done fast and, get on with it. So, and the final thing is a little bit on the mixed design of concrete, where if you can have no cracks and defects, maybe just now with all the nanoparticles mentioned by Prof. Hamida, might make it very interesting for the students to look into the research and all that. All right. So the first challenge is concrete quality and slump consistency. What I mean here is I'll show you a video of a concrete floor. A concrete has been supplied for us to do a floor. And if you look at the video, right, certainly this concrete is really, really wet, all right? Like I said, this concrete is actually looks like a self compacting concrete or self flowing concrete. So I always say that you're getting it has the same price as a normal concrete, but ended up you get, but it's not the true self-compact or self-flowing concrete, but with such bad concrete. Sorry, I hope you can hear me. Is all right? Some interruption.
Yes, we hear you.
Okay. You're right. All right. So these are the consequences of a high water cement ratio, right? The first thing is shrinkage crack. As you know, shrinkage crack would always many months, all right? Because as you know, it has the water escape from the within the concrete, and that's where the stress and strains will build up within the concrete. And being the concrete being very young, you might not have the strength to fight the stress and all that. So that's why for sure, any wet concrete that's delivered to the job site will have a lot of shrinkage crack. The second thing could be crease crack. You see a lot of spider cracks on the surface, all right? And this is not so much caused by the water, but because when it's so wet, what happened is that most of the time the workers have to sprinkle cement on the surface, all right? So when it's one way of sprinkling the cement is to suck up the water so they can go in and finish off the job early. So when you have too thick a paste, all right, and due to the difference of drying or the temperature, so the skin or the surface will always dry up much faster than within. As a result, it's due to the differential of shrinkage. That's why you have a lot of these cracks on the surface. But all these are not actually, I would say, structural, or it's just aesthetic. It doesn't look good, but it will never actually peel or delaminate. Okay, it's just unsightly. So the third thing is actually the surface can be very dusty and weak surface. All right, you got very low abrasion resistance and all that. And of course, finally, is that your compressive strength would definitely drop, as you know, right? Concrete, the more water you have, all right, for sure, your strength would definitely drop. Okay, so these are the consequences of having very, very wet concrete. Okay, all right. So the second challenges is supplying concrete with good workability. What I mean here is either the concrete is too wet or too dry. You see, when the concretes are too dry, especially you can see from this picture, right? The workers would definitely have to add water, isn't it? And I always say that if you are a good technician or you knows about concrete, it's okay to add water, all right? But you must measure it, all right? Put it in the bucket. If you know, maybe you add 10 kilo of water per meter cube, you might lose like probably 2 or 3 MPa, but not using a hose. You can see that this is unlimited, all right? And you don't know how much water you add in and all that. So end of the day, you get a very wet concrete. So my recommendation is always good to have some super plasticizers at a job site on standby. You find it's really too wet, you can always dose in, all right, with the technician's advice how much you could add. So this is the picture of what happened. They add water, right? So these are the earlier batch, right? They have done, right? Looks good, workable, and this is after adding water. You can see how wet the concrete is. So another is beside all the consequences I mentioned earlier. Sometimes because this concrete is already started, will definitely set much faster, and this being wetter, it will definitely set slower. So as a result, you might have what we call a cold joint, right? Normally, cold joint are caused by disruption or delay of concrete supply, isn't it? Let's say if you place this concrete right? After 2 or 3 hours, there's no supply, and then the fresh one comes in, and you know that the fresh and the old hardened concrete would not intermix. As a result, after many months, as the concrete starts to shrink, you tend to have a crack line appearing there. So these are the reason why you need to have very good workability of the concrete, so that the workers don't add in water. All right. Okay. Okay. The third challenges is actually, as you know today, all these supplementary cementitious material, the common ones are the fly ash, slags, and the silica fumes. All right. And especially for students, you know that all these ashes are based on the dump site, and today to substitute the cement, right? So with all these supplementary cementitious material, you actually enhance properties of the concrete, right? So I'll just mention briefly some of the advantages and disadvantages of using SCM, right? First thing is it reduce cement usage, all right? As you know that when I started in construction, at that time, everything is ordinary Portland cement, right? OPC. So, for example, 1 meter cube of grade 30 concrete, you might have 300 kilo of cement. But today, they might add as much as, say, let's say 30% of fly ash into it. So in other words, you meter cube of concrete, you might have like 200 kilo of cement and about 100 kilo of fly ash. So because of that, you know very well that when production of cement, you create a lot of carbon dioxide, isn't it? Every ton of cement you produce is equivalent to almost a ton of carbon dioxide into the air. So by using all this, you help. We talk about sustainability, one thing. And the second thing is it actually reduces heat of hydration, right? Especially when you're doing very thick slabs. Right? When I say thick slabs, maybe it's like about a meter thick. So when you do any thick concrete, what happened? The heat of hydration, we use OPC, right? The core of this slab, I think in the next picture I'll show you there. For example, you're doing, let's say this is could be a pile cap, it could be 1 meter thick, or even a basement slab. So what happened when you're doing such a thick slab using OPC? The heat generated within or in the center of the core can probably easily reach 70 degrees C. And your ambient temperature, right, let's say is 30. So there's a difference of 40 degrees C. As a result of that, okay, what can happen is that you will get a thermal cracks, right? So most of the researchers say that if you got anything more than 25 degrees C between the core of the slab and the ambient temperature, you will have thermal cracks happening. So besides that, another thing can happen, another type of crack can happen is called delay entry guide formation. As you know, during the cement hydration process, a lot of these entry guide, they are kind of like crystals starts to develop. But because it delays the entry guide from forming. Okay. So what happened is that after many years, not around 10 years or so, in the presence of moisture, so this entry guide, when they're in contact with this water, that's where they will start to crack. That's a little bit why adding all these would definitely help in all these thermal cracks. All right. So at the same time, it will also create cracks. I'll talk later, right? So these are always the plus and minus point of it. So of course, you know very well the enhanced properties of PC. The highest strength you can get is probably like 60 MPa, right? but you add in, you wanted to have 150 or UHPC, you have to add silica fume, right? As you know, silica fumes are about 100 times finer than cement particles. So that's why it enhances the properties of the concrete. Okay, a little bit about the disadvantages of using SCM, right? This is sharing my experience, right? Of course, first, you know very well, it delays the concrete setting. Normally, if you use ordinary Portland cement, it would take like probably 3 to 5 hours for the concrete to achieve initial set. What I mean by initial set is that you can actually walk on the concrete, your foot wouldn't sink in. That's where you can go in and start, doing your work and all that, your power flow process and all that. So, but if you use, let's say 30% of fly ash in the concrete mix, what happened, you can't go in within 5 hours. It would delay the setting probably 8 to 12 hours. All right. So it's not very good for people like us, right? Waiting for the concrete to set. So that's one thing. Delay setting. The second thing is, of course, the composite strength gain is, you always test your concrete at 28 day strength. But because of the, let's say, fly ash being added in, that's where you test your concrete at 56 days, right? And end of the 56 days, you always get a higher strength than the 28 days with the OPC. All right. So the third thing is very important. It actually causes thermal cracks. This is something where I don't know how many of you understand, because for me, being a very practical person, so it's just a picture to show, all right? Spend this entrance porch in this UITM university, and we did the concrete slab, right? As you can see, this is the shape, right? Because the
Dr. Zach? Dr. Zach, any problem? Dr. Zach? Paisan?
Ya, Pak Jiman.
Dr. Zach ada problem dengan dia punya line ni?
Ya, dia ada connection problem itu.
Oh my god.
Boleh next keynote?
No, okay. Nanti dulu, ya. Nanti saya cuba contact Dr. Zach. Any problem? If he have any problem, good then. So I think if possible, I think better we try to open for Q&A to Prof. Hamidah if we have any question from the participants. Okay. Before Dr. Zach join us back, so I think better we open the session for Q&A to Dr. Hamidah, to Prof. Hamidah. Any question from the participants to Prof. Hamidah?
Yeah, I got a message from chatting.
Okay.
He asked what is the drawback of the smart concrete.
Okay.
Of course, for every innovation and new invention, of course, first is cost. And second is understanding of the principles behind is a issues regards to the smart materials. Cost definitely. That's why smart materials still cannot penetrate into the market because of cost. For example, nano material, carbon fiber is a not cheap materials. It is a very expensive. And for understanding like using of BIM, even though the use of BIM now has been popular, but still only a very big company only able to adopt the BIM. This is because of the tools, the IT, the high end of computer, and only the IT savvy understand how to adopt with the BIM. I think that is the answer lah. What the drawback of all the smart materials and the new technology.
Okay.
Mm.
Any more questions?
Yeah, Professor Hamidah.
Yeah, yeah. How are you, Dr.
Okay.
Lee? Long time no see.
Yes, indeed. Congratulations on your presentation on nano clay and nano silica. I wonder how did you synthesize nano silica and nano clay at UITM?
Oh, no, actually, I'm only look on nano clay.
Okay.
We not synthesize. We bought the clay from a local supplier. I
Okay.
can't remember the name of supplier. Then we just grind to the nano size.
Okay.
Just a grind, and then we heat calcine at almost 700 Celsius to 900 Celsius for 24 hours.
Okay.
Mhm.
I remember 17 years ago, I managed only to make use of the jet mill to go down to 10 micron. In order to achieve 10 nanometer, I have got to send the sample to Germany Buller to get down to 10 nanometer. So
Okay.
if
Why Germany? Why Germany?
exactly, because those days I have that contact, you see, so it's very costly exercise. So
Yeah.
if facilities are available in local universities or other research institutes, it
I
will be
think synthesizer.
yeah,
I think Sirim. Sirim have Dr. Lee.
yes,
Sirim.
yes,
Actually, we intend to collaborate with Sirim to produce the mass production of nano clay.
yes,
At the moment, UITM, we just grind with the zirconia ball, and
yeah,
then we study the optimum duration and the temperature burning. That's all. We are by grinding only, not by
yes.
synthesizing.
Is it in the form of colloid, the nanoparticles? They mean in liquid form, so
No, no,
that
no. It's a
not
dry
is.
powder. It's like a cement.
Oh, okay, okay, great.
It's like a
So,
cement.
yeah, so we're looking forward to go into details later on. Thank you very much.
Sure, sure, sure. Okay.
Okay,
Okay, I
Prof.
think we can
Okay.
back to Zach now.
Yes. We proceed
Okay.
we back to Dr. Zaid to continue his presentation. Okay, Dr. Zaid.
All right. Okay.
Okay, Dr. Zaid, please continue.
Me?
Yeah, Dr. Zaid.
All right.
Okay.
Sorry about the lost connection. All right. So I just talk about, why do you have this thermal crack, all right? Like I mentioned, because as you can see, this area here is under a shade. It's not exposed to the sunlight. So the concrete is cooler here. Whereas here, the concrete is exposed to the sunlight, it gets heated up. So when it heated up, what happened? This concrete will tend to expand. All right, and being just a few hours old, the concrete is very, very young, and that's why when the stress starts to build up, it's more than the strength of the concrete. That's why we get a crack along here. Right. So this is same as sometimes I was called to investigate when they do external casting of floor slabs. Certain panel, there are cracks. Certain panels, there's no crack, all right? So first thing what I do is that I look at their concrete mix design, and I for sure I will see 30% of fly ash there, right? Not say it's no good, but it's for open casting. I always advise them, if you want to use, okay, let me finish the story. So what happened when you have 30% of fly ash, and when they cast the concrete, let's say it's about 10 o'clock in the morning, all right? By the time they finish, probably it's like, 3 or 4 o'clock. And that's where the sun is the hottest, all right? And same principle, because the concrete will want to expand when it gets heated up, right? Plus the heat of hydration generated. That's why the concrete cracks, all right? But when I check on some of the casting where they start in the late afternoon, let's say 3 or 4 o'clock in the afternoon, and they finish like midnight and all that, and these slabs, we don't see any cracks, okay? So there's one reason why when you're doing casting of concrete open using blended cement, you got to be careful, all right? So these are some of the disadvantage. Okay, then like I say, it's fast set. Normally fast set you will get high early strength, right? But the problem with fast set concrete, you can only use it mainly for repairs, right? Why? Because it's only a small job. And all this repair mostly are either pavements or roads where they want to hack out the or damage concrete, and within a few hours, all right, they want to open up again for traffic, right? But that's the reason why because it is set so fast, you don't have enough time to do, for example, a new concrete road, all right? So there's not enough time for you to place, to vibrate, and screed the concrete, and finally texture the surface and all that. So you just don't have enough time, all right? So the other thing is, it's very, very costly, right? Let's say for a normal concrete, 1 meter cube, it might cost like 60, 70 USD, right? For high strength and fast set repair concrete, it might cost you like as much as 2,000 USD per meter cube. So we see the big difference, right? And of course, the third thing is there's a lot of demand, right? Because everybody wants to do their work faster. They want to turn over their form work, especially the precast people. So there's a lot of demand for fast set concrete. But because of the price and the fast setting, so I always tell the researchers, right, if you can, you should work on, this type of fast set for not only for repair, but for new projects, that'll be good, right? So I think the researchers today, the latest what I heard is that they can do like 20 MPa within 8 hours. Okay, yeah. And the price is like only 1/4 I was just mentioned, so I hope that you all will continue looking into all this research. So, for example, like this repair, all right? Why this repair failed, right? I mean, it cracked up again and all that. Just to give you a few seconds to think, right? I don't know, since anybody wants to give it a try, why this repair fails, if you can unmute them, right? Anyway, it doesn't matter, all right? Let me finish it all, right? So from my experience, the one of the main reason that this repair failed, because unless the concrete is very weak, that's one. You use a very low strength concrete, all right? You simply just mix it aside and just pour it. You can't. For repair work, you need to have very, very special concrete. So the second reason, it could be that even they use a good material, right? So what happened is that they open up to the traffic too early. That means before the concrete actually achieve the strength to take the load, they already open it up, So that's the second thing. That's why worker doesn't understand, all right? And the third thing could be whatever repair you do, don't do it during a hot weather, all right? Because hot weather, you know very well that the concrete would set much faster, and anything that's fast setting, if you don't have the right chemical, it would actually cause us crack. So this could be some of the reason. Okay. So challenge number 5, the final one, is actually to design concrete free of cracks and defects, which is very, very a real challenge. It's not easy, right? Like us as a floor specialist, we have been looking into a lot of solutions. We try a lot of materials, and finally we are almost there, right? So try to use as low water C as possible, right? And you all know very well that if you don't have enough water, you also will cause autogeneous shrinkage crack. So playing around with this is what we found is for the mixed design. If you can, all right, keep your water between 145 to about say 180 kilo per meter cube. That's subject to your cement again. All right, that's very important. All right. Another thing, even too much of cement could be bad, because if we always try to cap our cement content below 400 kilo per meter cube of concrete. The reason is if you've got any higher cement than that, it might cause curling of floor slab. The slab will actually curl up. So that's another type of defect. So the second thing what you should do is to add in a shrinkage compensating agent, right? It could come in a liquid or a powder form, all right? So what this shrinkage compensating agent does is, when you add it into the concrete, all right, what it does is for the first probably a week to 10 days, it would actually expand very, very slightly, or it would prevent the concrete from shrinking. Right? There's no very well, right? If you don't cure your concrete well, the water starts to change, right? Concrete will start to shrink. So when you add this shrinkage compensating agent, what it does is prevent the concrete from shrinking. And during this, let's say 7 days, all right, what it does is it actually allow the concrete to gain strength without any volumetric change, without any stress and strain build up. So after the 7 days, it will behave like a normal concrete. So this is what happened. That's why we have tried a lot of this, and it actually works if you do it right. So that's the second thing you can look into. And the third thing is it costs a little bit more. Just now for the anti-shrinkage compensation agent, it might cost you like probably $20 USD, right? And the third thing is to do a hybrid system. What it means is that in addition to your conventional rebar that is designed for the slab, you actually add in fibers, can be steel or synthetic fibers into the concrete. And you know very well that all these fibers are three-dimensional within the concrete, and that's what it helps to hold all the cracks together, right? And you know very well that when you add in steel bar into the concrete slab, it's basically to control the cracks, all right? Besides taking the load, but the main purpose is controlling the cracks. But it's very difficult to position the rebars where they should be. In other words, sometimes the steel, the concrete cover is too much, For example, you should have a 50 mm concrete cover, but due to shoddy workmanship, the cover could be even sometimes 100 mm. So that's where you got a thick mass of concrete, and when the concrete shrink, that's where it starts to crack. So these are the reasons why you'll find it very difficult to control cracks, all right? And third thing is, you don't restrain the concrete, all right? If you can do any concrete structure or slab without any restraint, right? Restraint means it could be caused by, let's say, undulation in the sub base, or there could be beams or anything that actually prevent the slab or the concrete to move freely. That would reduce a lot of crack as well. So, and again, like Pro Hamida was saying, with all these nanoparticles, maybe somebody can come up, with research and try and error to look for a concrete that can, prevent all these things from happening. Right? So lastly, it's just a little bit on some of the common concrete defects that contractors or owners always face, right? So as you can see, crack is always the main concern. As you can see, these are a lot of cracks appearing. So when you see this crack,
Zach, okay. Does that your
trust me.
Does I cannot hear you. Because I think your network is not clear.
Top
Zach, we cannot hear you. I think Dr. Zach also have a networking problem again. So I think better if the participant have any question for Dr. Hamida, I think you can ask him question or give the message. Okay. Okay, Pro Hamida.
Yeah.
Okay, I have one question about the nanomaterials.
Okay, yeah,
okay.
Dr.
Okay, so normally the people always talk about the advantages of this material. That means the special thing about the nanomaterials. But could we know what is the disadvantage of the nanomaterials? That means what's the potential of what are the potential harmful effect of nanoparticles in the concrete?
Definitely nano, as I mentioned in my presentation, because it's very small, it can fill up all the pores in the range of millimeters up to the nano. So you will improve the durability of the concrete and can produce a very, very high concrete without too much cement inside. That is the one major advantage. Disadvantage, of course, nano material is very, very expensive. Like Dr. Lee said, he had to send to Germany and the cost is very, very expensive. That's why nano still not so popular. And then in my research, that's why I and my PhD student try to use a clay where we can get clay from locally. We can buy a clay, not so expensive, but we have to grind. And the grind also take a very long time to produce a very fine, get the nano size. Yeah, of course we did the study. We try to determine the optimum duration. We have to determine the optimum temperature to get the most pozzolanic nano. That is a disadvantage. Cost and the process of producing nano is not cheap and it's not easy either.
And any potential harmful effect?
Potential in terms of what, Dr. Ziman?
yeah, in terms of, potential harmful effect of nanoparticles when,
Harmful.
yes, harmful.
So far within my knowledge, there is no hazard
Okay.
due to nano. Only
Okay.
the cost. Yeah.
Only the cost.
Only on the cost. Very, very expensive.
Okay.
When you talk about nano, it's based on gram, not kilogram. The cost is based on gram.
Okay, so now Dr. Lim back. Dr. Zach
All
back
right.
now. Okay, so
Okay.
Dr. Zach, are you okay?
Yeah, sorry about all this.
Okay, Dr. Zach, you have another 5 minutes.
Yeah,
5
okay.
minutes for your presentation, huh?
Yeah, this is the last slide. All right, okay. All right. The other thing is random crack. As you know, normally random crack is sorry. Yeah, normally random crack is caused by if you don't have allowed contraction joints, or when the slab panels are too big and all that. So you're bound to have all this crack from happening. So you must control your panel size to avoid all this random cracking. Right? Of course, this is a plastic shrinkage crack, right? Okay. Somebody got to mute themselves. All right. Okay. So for plastic shrinkage crack, normally it's caused when the concrete is still not hardened yet, it's still green, and due to the direct sunlight and the strong wind, the surface drying up too fast, it's always start to crack. Okay, so you must know how to design a concrete with a little bit of bleeding, or you miss or fog the surface while you're doing the work. All right, and of course these are more of the contraction joint problem. Okay, and you know that actually all concrete floor slab will curl up, right? All right, all concrete would the thicker they are okay. When the thinner slab, they will always curl, as you can see, right? After the two slab, when they curl up, you see a big gap. Delamination, right? It always happens. Delamination, there's many causes of concrete delamination. Basically, they are always actually caused by, today, if you're talking about cement sandscape, it's because the way they do the making is not right. And the percentage of the mixture design is not right. Instead of like 1 part of cement, 3 part of sand, they might put 1 part of cement and 6 part or 10 part of sand to save cost. And they do it very, very dry with almost no water in it, right? So these are some of the causes of delamination. And I've explained earlier, because the surface always dry up much faster than the internal. And last thing is slab like this, where they are kind of basement and roof leaks. Leaking is always a big issue. And that's why a friend of mine who do repairs says that with this, right, they make a lot of money. Without all this problem, they cannot survive. Right. So sometimes it's also good, to have some of these defects. Okay. So in conclusion, I say that knowing concrete, it will always harden and crack. All right. So let's do more research on concrete mix design. All right. With better working properties, good workability, or a minimum cracks and distresses, like, and repairs and all that. So, okay, thank you very much for your attention. All right. So, please, if there's any questions, kindly forward to us. Thank you for listening. Bye.
Okay, Taisan.
Okay, thank you, Professor Lim. So there is QA in Zoom chat. Is there any temperature effect or change in using smart concrete from Mansi Sharma? That's first. Second, how nano silica can prevent the degree of harmonization of concrete? From Shahrul Hisham. Prof. Hamidah or Prof. Zek?
Sorry, I didn't answer. Couldn't listen to your question.
Okay. From Zoom chat, Prof. So there are two questions from Mansi Sarma and Shahrul Hisham. First about the temperature effect in smart concrete, and second about the nanosilica.
I think I answered the first question on temperature effects. We are talking about smart concrete. Smart concrete, in definition, is the concrete that very sensitive to any external stimuli like temperature, stress that I mentioned in my presentation, like moisture, pH, electric and magnetic fields. And of course, this smart concrete will detect the temperature effects. All the sensor, because when you're talking about smart concrete, is incorporating sensor in the concrete to detect all the external stimuli, including temperature. Of course, temperature will affect, and no, the temperature change will be detected by this smart concrete, and of course we can relate to the parameter or whatever we measure in the concrete. That is my answer for a question from the chat. Is it answering Ehwan? Prof. Ehwan?
Yes, Professor.
Is it the question? Okay, the second question.
Concrete from Mansi Sarma is okay. Thank you, ma'am. From Mansi Sarma.
Okay. The second question from Shahrul Hisham. Shahrul Hisham, how nanosilica can prevent the degree of carbonization? Carbonization, is it the process where carbon dioxide penetrate into concrete and cause corrosion? Is it? I presume that is the question from Shahrul. And of course, nanosilica can prevent that, because that nanosilica will fill up the pores in the concrete and definitely will stop the carbon dioxide from atmosphere from entering to the concrete and stop the carbonation. That is my answer for the second questions.
Okay, thank you, Professor Hamidah. Maybe
Oh,
Professor Zek.
No, there is another question, Ikhwan. Can I contact you on nanomaterial for concrete? Of course. Of course. But how you can get my email, or I don't know how to give my contact number to this Ham Peng Heng.
Okay.
Can I give the address in this chat, Prof. Iwan, or how?
Yeah. We can share your email, Professor.
I can type my email in the chat.
Yeah. You can type.
Okay, I type now. Okay. Okay.
Professor Hamidah, I have another question. Is it okay on translucent concrete? Is any work done at UIT?
Actually, I don't work yet on translucent, but is this the area that I'm interested to look for, Dr. Lee?
Okay, great. Okay, thank you.
I think, Dr. Ehsan, I think we can open for one more question if we have.
Yes, I have one question for Dr. Hamida.
Okay, Prof. Okay.
I'm
Yeah, Dr. Arif,
Professor,
please.
I'm Professor Dr. Arif from Pakistan, and I have
Hi, Arif.
Thank you for your very good and valuable presentation. And I have one question for you that this translucent concrete is really very good in terms of its use in dark areas, basements, and many other areas. But I would like to know.
Translucent.
Yes, I would like to know that to what extent the fibers which you are using in this concrete are creating impact on the strength of concrete. So this is my question. Please reply.
Dr. Arif, again, what is your question? What type of fiber used for translucent?
The translucent concrete, you made translucent concrete by introducing some fibers, and how these fibers are creating impact on the strength of concrete.
Oh, okay. Actually, I'm frankly said this is the area where I'm interested. I'm still doing a review because I don't start any work yet. But based on my literature review, it says that we are using optic fiber.
Yes, yes.
Optic fiber. There are a lot of optic fiber, but this optic fiber you put inside, slit inside the concrete, and this optic fiber can produce a light inside the concrete.
Okay, thank you.
Optic
But
fiber.
okay. But my interest was to know that these optic fibers are creating some contribution towards negative or positive sides of concrete strength or not. This was the question.
Oh, that one, frankly, I'm not look into the
Okay,
effect of this optic
okay.
fiber
Thank you,
towards the concrete properties.
thank you very
Yeah,
much.
yeah. Okay,
Thank you,
Dr. Arif, thank you.
thank you, thank you, thank you very much.
Okay, Dr. Ehsan, I think better we stop this first session.
Okay, Professor.
Okay, we can go to another session.
We give applause to Professor Hamid and Professor Zekli. Thank you very much. So, Prof. Haziman, we can.
Okay, yes.
Next keynote.
Yes. So for the second session, we will have Professor Amit Kumar from Delhi Technological University, Delhi, India. And the second presenter will be Professor Dr. Lim from CPU Hong Kong. Okay. So is it Prof. Hamid?
Good afternoon, everybody.
Okay.
Here.
Are you ready, Prof. Hamid?
Good afternoon.
Good afternoon, ma'am. Good afternoon, everybody.
Okay, so before Prof. Hamid give his presentation, I want to produce Prof. Hamid first. Okay. Professor Hamid has more than 20 years of hand-on experience, currently working as a professor at Department of Civil Engineering and Associate Dean, Outreach and Extension Activity, Delhi Technological University, Delhi. His main areas of interest are geotechnical engineering, strength and deformation behavior of rocks and rock mass, okay, pavement engineering, and modern and sustainable construction practice. He has qualified GATE from in year 1996, having all India rank was 162, IES 2000 and 2002, having all India rank was 33 and BPSC 1999. Okay, he has more than 50 research publication, okay, at national and international level, okay, journal and also conference. So today he will present his paper. He will share about the sustainable and economical concrete India case study. So I think I will give to Professor Amit for your presentation. Okay, please, Prof.
Yeah. Can you allow me to say? Yeah. Whether my presentation is visible to all?
Okay, clear.
And I'm audible also. So from India, you can hear my sound in Indonesia and Malaysia and many countries. So namaskar to everybody. I am very glad that I have been invited for very good international seminar or workshop, that is CSM International Webinar on Construction Materials in Greenation era. See, the professors or the speakers who have talked before me, they have given you a fairly good idea about the things, and I will be building on their concepts only. I will be discussing about the supplementary materials, cementitious materials and all. And I will be discussing about the Indian case studies where we have implemented this, and the worry the earlier professor or speaker was having about the cracks and all, how we have come out with all these difficulties. And in the topographical regions of India, where the summer the temperature is more than 50 degrees centigrade, and it varies from 20 to 50 degrees centigrade, how we have used the good sustainable construction practices, and how we have controlled these things, that I'm going to discuss. As I have been introduced, I am Professor Amit Kumar Srivastava. I am a professor in Department of Civil Engineering, Delhi Technological University. So my topic will be sustainable and economical concrete, Indian case studies. So the outline of my presentation will go like this. I will be discussing about the introduction, sustainability, and cement manufacturing process. Now, how to reduce the use of OPC in concrete, ordinary Portland cement in concrete, then the role of admixtures, and then saving in resources, a case study that I am going to discuss. The advancement is bound to happen. It is the law of nature. So when the people were advancing, that time our construction industries were also advancing from the log to that brick masonry or stone masonry structures, wooden structures, then to the steel structures and concrete structures. And now you will surprised to know that even though the steel structures are better in performance, in India, concrete structures are more preferred. And if I'll say in world also, then I may not be wrong. The concrete structures are more in demand, more in use because of the flexibility, because of the ease, and because of the manpower, trained manpower available on this area. So now if I see that whatever I'm going to talk about here, because I'm talking about the Indian case studies, then I will be just seeing that if you see the world cement production in 2018, China is the first with the 57.3% resources, with the 57.3% resources, and we come to India, there's 6.2%. And if you see, China is the world most cement producers, and about 1/10 is the production by the India, and that is 6.2%. And we are the second largest producers and user of the cement in India. And it is not, we have to surprise that because we are a developing countries, and more cement demands are there. As I said you, that more and more we are going for the construction by the reinforced cement concrete. So more and more cement demands are there. So we are at the second in the world. Similarly, if you see the share of different industries in carbon dioxide gas emissions, and you can see here the cement industries alone, the cement industries alone is producing 6.9% carbon dioxide emissions of the total carbon dioxide emissions global. And if you see the trucks, the whole trucks of the world is producing 6.1%. It means what? The cement industry is producing the carbon dioxide gas, which is more than what is all the trucks in the road in 2017 has produced. Now, if I talk about that housing shortage of India, see, the housing shortage in India, if you see, according to HUPA is the Housing and Urban Poverty Elevations of, that is the ministry sectors. So they said that in 2018, the housing shortage was about 41%, because 1.9 crore houses are short for the people of India. And this will increase to 59%, and this is 2.6 to 2.9 crore units we required in 2022 to fulfill the demand of the people of India. Now you see, 59% shortage we are having, and as I said you, mostly we are going for the constructions of the concrete structures. And if I'm going for the concrete structures, so lots of carbon dioxide gas emissions will be there. Now, this is the background of my study. Then we will discuss what is sustainability. And as you know, that World Commission on Environment in 1987, they decided they had defined the sustainable as that which meets the needs of the present without the compromising the ability of the future generations to meet their own need. So what I may want to say here, we should not explore our natural resources in such a way that our coming generations will be deprived of this one. So our cement, because I tell you now in India we are having the shortage of raw materials to make good concrete, good cement, and sometimes we are procuring it, we are exporting it from Pakistan, China, Korea, so many places we are exporting it. And see, 59% of the development we have to do. So we are lagging also. So now how to use this precious material in such a way that I can preserve that material for my future generations, and how this cement concrete industries, what methods we can implement to reduce its use. That is the topic that I'm going to discuss today. So now how I can have sustainability in construction. So the best way is what? You have to use less and work more. Less quantity, more work will be probably the better answer of these questions. So if I'm having the less quantity, using more, our carbon dioxide gas emissions will be also less. And moreover, I can preserve this beautiful raw materials for the coming generations. So I'm afraid that if we are not doing it, then sometimes I will see, or coming generations will see, that cement in a museum. So now how to achieve it? So there are various ways by which we can achieve it, and the best way is that deliver more using less, like reducing concrete usage index by using very high and super high strength concrete. And in India, I'm trying to implement this since last 10 years, and the people have changed their mindset from simple M25, M30 grade of the concrete to M80 or M100 grade of the concrete. So higher the grade of the concrete, the cylinder, the sections will be there, and cylinder sections, the reduced sections will have the reduced concrete, and less concrete can construct more. The second thing what we can do, we have to use the supplementary materials like fly ash, GGBS, microsilica and all as per the requirement, because microsilica is very costly. So normally we recommend that the microsilica should be used only for high grade concrete. And after all, see, whatever you are doing, you have to have the best resources and best technology to use it. If you design properly, if you use very good quality of the material, ultimately, if the handling at sites are not good, you are not going to achieve anything. So best technology and resources you have to use. Now, if I come to this slide, you see how to achieve it: reduce, reuse, recycle, and recover. And mostly, these are the four principles of environmental engineering. And mostly the concept, whatever I'm going to discuss here, it is reduce and recycle. I'm preventing the material to going into the landfill sites. So I am trying to use the waste material for the concrete productions. So what I want to reduce here, I want to reduce the use of water, potable water, used for the concreting and curing, So we are having the scarcity of the water, good drinking water, and whatever the water you require for the construction, for making the concrete and for curing, they are the good quality water. So how to reduce first the water requirement in the concrete, and then reducing the use of raw materials like ordinary Portland cement and use of proper technology, so that if I am doing it, it is better implemented and your structures are defects free. Now, I will give a brief idea, because I think that some students or some research scholars are also there in the presentations from India and from the different part of the country. So I just want to discuss the different cement manufacturing process. If you see, if I make cement, I require the raw materials which contains the calcium. And if you see, the calcium percentage requirement is about 60% by weight. And this 60% we are getting mainly from the limestone or calcium carbonate. Then 20% silica, 10% alumina, and 10% iron. So this limestones are burned at very high temperature in a large kiln for a temperature of about 15 degrees centigrade, 100 degrees centigrade, to convert this raw materials into the clinker. And during this process, what happened? There are too much carbon dioxide gas emissions are there. And the research says, and even we are at our universities are finding out the carbon index of each and every material of a buildings or of a infrastructure projects. What the research says that about 900 to 1100 kg of CO2 is produced. Is produced 927 kg is emitted, carbon dioxide gas is emitted. So if I produce about 100 or I say 1000 kg of cement, I'm going to produce about 900 to 1100 kg of carbon dioxide gas emissions. So averagely you can say 927 kg is emitted for every 1000 kg of Portland cement. And if I just try to generalize it, it means what I can say, 1000 kg of Portland cement will produce 1000 kg of carbon dioxide gas. It means 1 kg of cement will produce 1 kg of carbon dioxide gas. So if I am saving 1 kg of cement, I am reducing the burden of carbon dioxide gas emissions by 1 kg. So it is equal ratio. The cement, whatever the cement you use, and same carbon dioxide gas is going to emit it. Okay, and there's how much carbon dioxide gas will emit. It depends upon the technology and what type of fuels and all that is used in the process. Now you see how this carbon dioxide gas is emitted. Now I'm trying to explain this through a simple flow chart that is anybody can see. You can get in the Google also. So this is the quarry site. From the quarry, the excavators are excavating the material, and this truck will take this material to a crusher, where the crushers are there. Coarse grinding of the limestones are taking place here. Now this crushed material will go to the secondary crushers. Again, the fine grinding of this material is happening here. And then because we are doing with the limestone, so we are having calcium oxide here. So the different components to get that silica and alumina and all, we are having the clay and sand. Here the clay and sand is mixed to this. And then again, we are having the grinding mill where the grinding of these things are taking place. And then we are having this place is a preheating towers where these materials are getting preheated. And now these days, so many advanced technologies are there. You see the vertical types of preheaters are there. So preheating materials, these materials are getting heated in while it is passing through this surface, and now it is going into the kiln. You see, it is going into the kiln, and here the temperature is risen up to 1500 degrees centigrade. So the clinker is formed. Now this material, after this, it is getting down here, okay, and from here this material will come down here, and from here this material will move like this. So the clinker will move like this, and here the gypsum container is there where you put the gypsums, So gypsum is added to this material, and this material is coming to this silo. Now I tell you, the technology, the better part of the technology is that some of the heat, because it is a cooler where the material which is risen to a temperature of 1500 degrees centigrade is cooled. So whatever is the heat released from here, this heat is recycled here and it is going back for preheating of this materials. So somehow we are using our resources in a way that less heat we have to use. But even though the productions of 1 kg of cement produce 1 kg of carbon dioxide gas. Now you see, when it comes to here, there we decide that either it is a OPC or PPC or slag cements. So if it is a OPC, then directly this material will come to this silo. From this silo, it will go to the works, that warehouse, and where the cement bags will be prepared, and it will be carried to the sites. Or if it is a slag cement or fly ash cement, then here you have to use the concept of mixing this material with the fly ash or slag. So now you see, whatever the cement we are manufacturing, actually up to this point, it is an ordinary Portland cement only. The last point we distinguish, it is a OPC, PPC or slag or different types of cements. Now this process, the elaborated process, causes the emissions of the carbon dioxide gas at the tune of about 1 kg per 1 kg of the cement. Now, if I want to have the sustainable growth, so if I want to reduce the carbon dioxide gas, then what I have to do? I have to reduce the use of the ordinary Portland cements. So, and ordinary Portland cement, if I'm reducing it, it is not only reducing the carbon dioxide gas emissions, it is also saving the cost, because ordinary Portland cement is a costly material. So now how to reduce it? So kindly unmute. Mute yourself. Okay, so how we can do it? So for that, the admixtures are there which can reduce the use of the ordinary Portland cement, and the admixtures are classified in two ways, and I'm going to discuss the two admixtures here: the chemical admixtures and mineral admixtures. Now I will discuss the role of chemical admixtures, what chemical admixtures does in this whole process, and how it is going to reduce the demand of the ordinary Portland cement, and how it is going to reduce the water in the concrete, manufacturing of the concrete. So now you see, when you add water into the cement, this type of cement flock is formed. So you have the orientation in such a way that your edge-to-edge orientations are there. When you have the edge-to-edge orientations, you see a bigger gap are formed here. Bigger gaps are formed here. You can see here, bigger gaps are formed. Now what happened when we put the chemical admixtures to this? What it does, it makes the cement particles with the negative charge. So once the cement particles get negative charge, there is a repulsive effect, and whatever the flock, this whites are there, and in this white, when the water will come into this water will be clogged here. This water will be clogged here. So when water is clogged, means what? This water is not available for the reactions. So what we do, when we add the chemical admixtures to this, the cement particles get negatively charged, and they will have the repulsive effects, and the water which is trapped inside the cement particles and which was not participating in the reactions, now it is released and now it is available for the reaction. So now you see this diagram. So this diagram will explain you properly so how this water is getting released and this water is available for chemical reactions. So this is the main concept of the chemical admixtures. There are various other researchers and different persons has explained the same thing in different way and different theories. So this is the most easiest way I can explain the chemical admixtures and how these chemical admixtures are reducing the use of water into the concrete. Now you see our Indian Standard Code has given the diagram, and this you may see sometimes you will have for the European Code also, for American Concrete Institute also. So now you see for a given water cement ratio, you will get the given 28 days compressive strength. Now, if I say our water cement ratio is 0.5, and if I am using the 43 grade cement, then I will get 30 M30 grade of the concrete. You see, if it is 0.5, then I will get 30 grade of the concrete here. You see, 30 grade of the concrete here. So it means what? For getting a particular strength of the concrete, I have to keep my water cement ratio constant. Now, with the small calculation, I want to explain the whole concept. I'm considering that some of the students are also listening to this exercise, so that's why a small calculation I am telling you. And you will know that, suppose I'm considering taking the water cement ratio of 0.5, and you will surprised to know that almost the water requirement for a given slump is same either you are using M25 grade of the concrete or you are using M100 grade of the concrete. The water is same. And by keeping the water cement ratio as a constant, by varying the cement, I am getting the different water cement ratio, and by reducing the water cement ratio, I'm getting the higher strength. So that is the concept. So normally water required is 200 kg. I am just assuming. So it depends upon the what is the slump, what is the flow, what you require. It may vary a little bit, but whatever the grade of the concrete you are going to manufacture, and for the same workability and for same slump or for the same flow, you have to keep the water requirement as same or constant. So water requirement is 200 kg. So now if I say the water cement ratio is 0.5, then what is the cement I required? I will be requiring the cement of 400 kg. Now the role of chemical admixtures comes. So now we add the chemical admixtures. In the market, if you see, there are different generations of chemical admixtures are there. That is called a super plasticizer, or it is also called as a water reducing admixtures. So some admixture is giving you the water reduction of 20%. Some admixture is giving you the water reduction of 35%. Some admixture is giving you the water reduction of 40%. Or sometimes by varying the percentage of this admixtures, you can increase or decrease the water reductions. So now if I see the water reduction is 20%. So now if you see this calculation, and this calculation says that, so water required is 200, reduction is 20%, so minus 0.2 into 200, so it is 40, so 200 minus 40 is 160 kg. Now, see, if I use a chemical admixture, which is reducing the water by 20%, the water required will be reduced to 160 kg, and for the same water cement ratio, now for the same water cement ratio is a 0.5, so water is 160 kg, water cement ratio is 0.5, now the cement requirement is what? We got the cement requirement is 320 kg. Now suppose I'm using another admixture which can reduce the water by 40%. So if 40% water is reduced, then what happened? You see, water required is 200 minus 0.4 into 200. So 0.4 into 200 is 80. So now water required will be 120 kg. And you know, the water cement ratio is 0.5. So 120 divided by 0.5 will give you the 240 kg cement. It means you just see, by using the proper and good quality of the chemical admixtures, I can reduce the cement content from here 400 kg to 240 kg. So that is the things we can do by the role of, this is the role of chemical admixtures. Now, with the help of the example of a site, I will just explain you what we have done. Okay, we required a slump of 130 for a project, and we required to design the M35 grade of the concrete. So if I am using 130 slumps, I required 201.6 kg of the water. Okay, if I see the water cement ratio, if I keep, as IS code says that water cement ratio cannot be 0.4 more than 0.45, and for the practical purposes, I have used the water cement ratio of 0.41. So if 201.6 kg water required, water cement ratio is 0.41, then cement required I can calculate, and that cement requirement, then cement required is 491.8 kg. Now similarly, if I keep on calculating it, now what we will see, if I use the chemical admixtures, which can reduce the admixtures like 20%, they can reduce the water requirement. So 201.6 minus 20 into 201.6, if I'll do, I will get that what is the water reduction. And once I get the water reduction and water cement ratio, I know I can again calculate what is the cement reduced. So now I want to present this in the form of this. You see, if I am not using any chemical admixtures, so water required is 201.6 kg, cement required is 491 kg, so there is no saving. Now suppose I have used any admixtures which is reducing the water by 20%. So this 20% water is reduced, then water required is 161.3 kg. For the same water cement ratio, I will be requiring 393 kg of the cement, and then admixture required like something like this. So this is the calculation. We got the cement and water saving. So see, 390 kg, you see that 491 kg was the cement required when you use the chemical admixture. Now it is required 393.4. So now I got the saving in cement equals to 97.6 kg, saving in water equals to 40.3 kg, and if I multiply by the cost, I will be getting the cost also. Similarly, if I use, suppose, admixtures, that is called, mainly we are using here is the PC-based admixtures that can reduce the water by 40%. So if I come to that place here, so if we can reduce the water by 40%, then what happened? It is 201.6 minus 40 into 201.6. So I will get the 121 kg water, and water cement ratio is 0.41. So I will get cement equals to 295 kg. So now if I compare from 490 to 295 on kg, so I can reduce the OPC requirement by 196 kg, and I can reduce the water requirement by 80.6 kg. This is about 40%. But our IS code says that no, you cannot use the cementitious material less than 340 kg for M35 grade of the concrete. So if I am restricting myself as per the IS code's requirement for the durability requirements, then I will use 340 kg, then the reduction will be like this 140, and I will be using 1.7 kg of the admixtures. I said you, by just varying the dose of the admixtures, I can increase or decrease my water reductions. So I can have the net saving equal to 151 kg of cement. I can have the net saving of 61.6 kg of the water. This is about 30%. And if you say in terms of cost, 634.8 rupees in the Indian rupees. Okay. So now if I consider that this admixture that is 1.7 kg I am putting, it is also will invite some cost. So suppose 120 rupees is the cost of the admixture per kg. So if I calculate back, I'm getting net saving as 430.8 rupees. That is equals to $6.15 if I am producing 1 cubic meter of the concrete. So 1 cubic meter of the concrete, by using proper chemical admixtures, I can reduce the cost of $6.15. And at the same time, I am reducing the use of the cement by OPC by 151 kg. And if I'm reducing by 151 kg, so I'm reducing the 1 kg of the carbon dioxide gas in 1 cubic meter of the concrete. And in India, I will be discussing about the case study also. Many sites I have seen, they are producing about 500 cubic meter of the concrete daily. So if you are producing 500 cubic meter of the concrete daily, so you see in terms of money, how much you are saving daily, and in terms of carbon dioxide gas emissions, how much you are saving daily, and in terms of water, how much the potable water, drinking water, you are saving daily. So this is about the just use of the chemical admixtures. Now I will go to the next part. When I add mineral admixtures to this, as our previous speakers have said you, that is a supplementary cementitious materials. I will be also discussing about the use of this SCM. So now the supplementary cement supplementitious materials I will be using now is a fly ash. It is a waste product, and it is a product what we get from the thermal power generations. You see here we have the coal, and I tell you one thing more thing, that in India our coal are not good in quality for the thermal power stations because their fuel efficiencies are less. but they are very good for concrete constructions because their carbon to silica ratio is very high. This fly ash, whatever we are getting after burning in the furnace, that is about 1200 degrees centigrade and 1300 degrees centigrade, while generation of the power, they are having very high source of silica. So this fly ash are very good for concrete. Now you see what happens. Here coal is there, the furnace are there, here it is burned, and after burning, the larger size of the particles get arrested here, and the finer particles get moves from here. It is the electrostatic precipitors where they are brought down here, and that is called as a fly ash. And that is fly ash from the different sections. They are going to shallows, and this is a exhaust stock. So relatively better fumes we are sending to the atmosphere. Otherwise, if this electrostatic precipitors are not there, then what happened? The particle size which are getting coming out from the exhaust aspect will be high, and it will be settling down to the earth surface and harming the air pollution, creating the air pollution. So like this, we are getting the fly ash, and fly ash, it looks something like this. So I will be discussing about the use of this fly ash as a mineral admixtures, and another type of mineral admixtures are normally used is called a ground granulated blast furnace slags, and this is the product of, this material is a product of steel industries, and so that is also you are getting a waste material of the steel industries, and it looks something like this. Now what happens when we are using this type of material here? You just see when we use ordinary Portland cement, and when we add water to this reacts and form a gel called as a CSH gel, calcium silicate hydrated gel, and they leave calcium hydroxides unreacted. So when we put fly ash contains silica. Just as I said you, in India, Indian fly ash is having very good concentration of silica. So this free line, when reacts with the silica, it is again forming a gel, CSH gel, that is the secondary gel. So what happened? Whatever is the free line available, if you are using the fly ash, what it is doing, it is creating more CSH gel, and more CSH gel means what? You are getting the better concrete in terms of the strength, in terms of durability. Because this calcium hydroxide, if it is not used and it is left, it will cause calcination on the concrete, corrosion, and lots of problems. So if I am using OPC only, then this left out products is very dangerous for the life of the structures. So if I'm using this type of fly ash material, then what happened? This dangerous material, calcium hydroxides, I'm utilizing full. And once I'm utilizing full, so this is not available for the carbon calcinations and carbonations, and creating the durability effects to the concrete and corrosion to the reinforcements. Similarly, we have the another variety of the material that is called as a Portland slag cement. We are using GGBS here. So once OPC plus water I am adding, I am getting CSH gel, primary gel. Then again, this calcium hydroxide is unused. So now GGBS reacts with the water and they form CSH and silicon silicates. So what happened here? I am getting another CSH as a primary gel, and this SiO2 reacts with the calcium hydroxides here and form another gel that is called a CSH gel. So the quantity of formation of CSH gel is more and more, and we are getting better and better concretes. So like this, if I use this type of supplementary cementitious materials, they are going to not only get better strength, but it will give you the better durability also, because it is going to protect your reinforcements.
Dr. Prahamid, you still have 5 minutes more.
5 minutes? No, I will complete in 5 minutes. No problem.
Okay.
So I have discussed about that. Mineral admixtures. Now I am talking about the last part of my topic, that is saving in resources and case studies. See now, our IS code says that you just remember that 340 kg cements I discussed. 340 kg cements. So if you add this, it will be 340. So our IS code says that you can use 30%, 5% of the fly ash if you are using the normal concrete. If you are using the self-compacting concrete, you can use fly ash up to 50%. You see, so OPC 221, 119. If I am using 35% fly ash, if I am using 50% fly ash, then it is 170, 170. And sometimes if I am using GGBS, our IS could allow 70% replacement. So if I replace 70%, then OPC requirement is 104 to GGBS requirement is 243. You see, we have started from 491 and we can reduce up to 104. So now if I talk about the savings, so 35%, 50%, 70% savings. So you can see the savings because you see, we have started from 491. And if I talk about the saving only in terms of mineral admixtures, when no mineral admixture, your cement was 340 kg. When 70% mineral admixture, your cement was 104 kg. So net saving in cement is about 236 kg we are having if you are using 70% cement. Now, if you see cement saving in terms of, we are not using any admixtures, chemical admixtures and mineral admixtures, then it was 491, and if you are using GGBS, it is 104. So net saving, you can have the 387 kg of the cement, and similarly the water of 61 kg, because mineral admixture is not reducing any water. So whatever is the water is reduced, it is by the chemical admixtures. So that is about 30%, which is 61.6 kg. Now, if I see in terms of graph, you see, if I say the saving in and reductions, and I'm telling you, it is not saving in reduction of only carbon dioxide gas emissions, it is of the OPC cement also. And now, because you see, I have averagely I have taken 1 by 1 kg of cement, 1 kg of carbon dioxide emission saving. So if you see the rate curve, red lines, it is 0%. If you have using the chemical admixtures or mineral admixtures, it is 0, and it can go up to 80% reduction in the OPC requirement and 80% reduction in the carbon dioxide gas emissions. Similarly, percentage saving in water, maximum you can go up to 30%. So now this is the project, that is Clio County project at Noida, where this concept has been implemented. Now it is the project is commissioned, people are staying there, and we don't have any problems, and the building is performing well. If you see the bird view of this project, the project is looks something like that. And this project has been covered by Deutsche Welle, a German TV channel, about this project. And if somebody wants, I can share the YouTube video of that channel. Okay. So another project we have implemented this is the Gore City Greater Noida West projects. And this is as time is less, I'm not going to discuss about the projects, descriptions of the project, but here I want to discuss is that, see, Clio County projects, the concrete use index is 1.41 cubic meters per square meter of the area. I am using M40 self-compacting concrete there. Annual consumptions of concrete is about 0.11 million cubic meters per year. And if we don't use any admixtures, so the requirement was 690 kg of the cementitious product. So when we use the chemical admixtures, it has reduced to 612 kg. And when we 50% fly ash we have used, it has 306 kg and 306 kg. And if you see, cost of the cement, mineral admixtures, and everything is added here. So total saving in OPC cement is 380 kg per cubic meter of the concrete. Extra mineral I am adding is 306 kg. So if I add the cost of everything, I am getting total saving per cubic meter concrete is 24 USD per cubic meter of the concrete. And total saving in a year is $2.63 million per year. And if you see, carbon dioxide emission saving is 42.65 million kg of carbon dioxide gas is reduced per year. Similarly, the second project is the Gore City. And if you see the Gore City, as the time is less, I am just going to the last part of that to see the $3.29 million is saved per year, and you see the 51 million kg of cement is reduced per year. So this is my YouTube channel. This is my contact number. This is my so more and more this type of things that is there in the YouTube channels, what we are practicing in India and what we are implementing at different sites. So thank you very much for your question sharing. I will love to answer few of your questions if you have.
Okay, thank you very much for Professor Amit with your great presentation. So for Q&A, maybe we will open after Professor Lim finish his presentation.
Okay.
So okay, so now we proceed for the next speaker, which is Professor IR CW Lim from City University, Hong Kong. Okay. Before Professor Lim present his paper, okay, let me introduce him first. Okay, Professor Lim currently is a fellow of ASME, AFCE, EMI, and HKIE. He received a Bachelor of Engineering from University of Technology of Malaysia, Master Engineering and PhD from National University of Singapore and Nanyang Technological University, respectively. Prior to joining City University of Hong Kong, CTU, he was a postdoctoral research fellow at the University of Queensland and the University of Hong Kong. Okay, Professor Lim is also is a visiting professor at various university, including the University of Western Sydney, okay, Dahlia University of Technology, Guangzhou University of Science and Technology, etc. He has expertise in theory of plate and shell, dynamics of smart piezoelectric structure, nanomechanics, and symplectic elasticity. He is one of the editor for JMMS, okay, associate editor for Asia Pacific region for JVAC, associate editor for IJBC, subject editor for AMM, etc. And also on the editorial board of some top-ranked international journal. He has published one very well-selling title in engineering mechanics of technology, engineering mechanics, okay, and title, sorry, he has published one very well-selling title in engineering mechanics entitled Symplectic Elasticity, co-author with Yao and Zhong from Dalian University of Technology, as recorded in April 2010 by the publisher, World Scientific. He has published more than 300 international journals papers, accumulate more than 10,000 citations, and has a Google Scholar Edge Index 54. Okay, one of his papers, co-author with Gizang and JN Reddy, is a highly cited paper in JMPS and the most cited paper since 2009 in the journal, while another co-author with LH He and BS Hu was granted the IGSS 2004 to 2008 Most Cited Article Award. He was also awarded Top Referees in 2009. Okay, proceeding the Royal Society. Okay, Professor Lim is also a registered professional engineer in Hong Kong. Recently, Professor Lim is honored with the 2020 GN Eddy Medal, which is a very prestigious international award. Okay, so sorry. Please unmute your Mr. Ishaq Ansari. Please unmute your microphone. Mr. Ishaq Ansari, please unmute your microphone. Okay, So today, Professor Lim will present his paper entitled Production of Treated Recycled Aggregate and Basalt Fiber Reinforced Concrete for Sustainable Infrastructure. So now the stage I give to Professor Lim to proceed your presentation. Please, Professor Lim.
Thank you very much, Professor Haziman, for your introduction. Before I begin, I wish to introduce to you the co-author of this paper. He's a Mr. Behind me is a Mr. Wawiza Ahmad. He's a PhD student of mine. Okay, now I shall begin. Let me share the can you see the share screen? Okay, okay. So now I first of all wish to record my appreciation to the organizer for having given me this opportunity to share my work with my PhD student, Mr. Wiza Ahmad. The title of the paper today is it is regarding the production of treated recycled aggregate basalt fiber reinforced concrete for sustainable infrastructures, particularly in the context of the Hong Kong society, Hong Kong environment. Let me, yes. Why is it sustainable infrastructure? Let me just give a very common definition to you. By means of infrastructure which is sustainable, it means that throughout its life cycle, from the planning stages throughout to its operation until decommissioning, it provides social, economic, and environmental benefits. So this one shows the contents of my presentation today. I will first give an introduction to the talk, including the objective, background, and so, and it will be followed by treatment methods, sustainable methods, and finally some concluding remarks. Before I begin, let me just give you some idea. This is a project which is ongoing and it is not completed. So at the end of the presentation today, there will be no concrete conclusion, but it will be general conclusion because the project is still going on. So the objective of this presentation here is we will present recent statistics about increasing concrete production demands and its associated environmental and sustainability concerns. We also highlight the rapidly growing C&D waste and also the possible solutions for recycling. We will also overview the existing treatment methods and also the key challenges. And last but not least, we propose some sustainable and effective techniques for the improvement of weak properties of recycled aggregates. Let me just show you the production, the world production of some materials. As you may see, wood, steel, cement, and you can see that for concrete is about 7 times more than as is on about during about 2015. So the reason of concrete being used so commonly is because of the concrete properties, which is a commercially available, durable, high strength, thermal conductivity, and desired shape, and also the economical effects. And it is particularly, as you may see, in Hong Kong and also elsewhere in the world of the mega cities, concrete is one of the best and the most important construction material. And you may see in 1988, I remember just now one of the presenters also showed the similar cement production, which in China it constitutes about more than half of the production of cements in 2018. As the forecasted value for 2030 is given like this. So as you may see, China is one of the biggest. In fact, it is the biggest. It's the biggest cement production country in the world, and it constitutes more than half of it. The natural aggregates consumption worldwide. We'll see that the annual consumption of natural aggregates will grow to a figure of 62.9 billion metric tons by the year of 2024, which is a very large amount. Next, if we can see again that the construction and C&D waste has also drastically increased during the last few decades. US is the biggest production of C&D waste, which is about 69 million tons. No, 69 what? Oh, sorry, 569 million tons a year. The total waste, about 40% of the total waste is comprised of this C&D waste. As you may see, it comes from what? No, we will see that the construction industry, for the construction industry in China, they produce about 88 million of demolished waste in 2020. In the year of 2000. By the year of 2020, by the year of 2020, it will be about 2.6 billion tons. This is a remarkable increase. The advantage, for this reason, we need to think of a way of using recycled aggregates. The advantage of the recycled aggregate including what? Including solving waste, disposal problems, saving useful lands, preserving natural aggregates, preventing CO2 emission, and also the cost. We save money. In addition, recycled aggregate is also good. Has some limitations. On the other hand, it requires high water consumption. It also has porous microstructure, low mechanical properties, higher sinkerage, low durability, low acceptance for structural concrete. This comes to the second part of my talk. It's about the treatment methods. So in this part, I will first introduce to you the method of the method of removing the attached mortar, and also to improve the attached mortar, and finally we strengthen the structure by fiber reinforcing. We will go through one by one in brief. First of the method for removing the attached mortar is by autogeneous cleaning method. The attached mortar is first removed by placing recycled aggregate in rotating mill, and which has a diameter of 300 millimeter and a depth of about 500 millimeter. And it is collided against surrounding particles and followed by water cleaning. This method is less effective in removing the attached mortar. The next method is by the mechanical grinding method. The attached mortar is removed by crushing and ball milling process, which is similar to the Los Angeles abrasion test of aggregates. Micro cracks appear on the surface of recycled aggregates, and the mechanical properties and durabilities are compromised. So this method also has some limitations. We may also modify this method by thermal heat treatment. So this comes a third method, which is like thermomechanical grinding. There are two stages. First, the aggregate are heated to a temperature of 300 Celsius and then mechanically grinded to remove the weak ITZs. It produces high quality of recycled aggregate, but the problem is it demands high energy requirement because it needs heat treatment before grinding. The other method of removing the attached mortar is by acid treatment. Various acids like sulfuric acid, hydrochloric acid, phosphoric acid, and also acetic acid are used to dissolve the hydration products and weaken the ITZs. It improves the quality of recycled aggregates. A large-scale implementation, safety precaution, and high water demands are the key challenges. Of course, we have advantage and we also have disadvantage of the methods. The other treatment method is by improving the attached mortar. The first one is the polyzona slurry. Mineral admixtures like fly ash, silica fume, GGBS are used to fill the pores and to reduce the calcium hydroxide content. It will significantly improve the microstructure of recycled aggregates. It is environment friendly and sustainable. It is a sustainable approach. The second method is by polymer emulsion. Polymer solution is, in this case, polymer emulsion solution is utilized to coat the recycled aggregate surface, which fill the micropores and micro cracks. It reduces water absorption of recycled aggregate significantly. However, it is less effective in mechanical properties enhancement of recycled aggregates. The other treatment method is by biodeposition of calcium carbonate. Microbicarbonate precipitation is based on natural process wherein bacterial cells produce inorganic materials as part of their basic metabolic activities. The inclusion of calcium carbonate improves the microstructure and reduces water consumption. Some chemical reactions properties are presented here. One other method is carbonation treatment. In this case, carbon dioxide reacts with hydration products of cement and forms calcium carbonate. The resultant calcium carbonate improves the microstructure and reduces the water absorption of recycled aggregates. The last treatment method for improving attached mortar is by sodium silicate solution treatment. This treatment is almost similar to the polymer emulsion treatment, in which silicate-based solutions are used to coat recycled aggregate surface. It is effective in blocking the capillary pores, but it is less effective in resisting chloride ions penetration and water penetration, and it leads to higher alkali content in concrete. Now, we move to another treatment method, which is by fiber reinforcement by using fibers. We can have steel fiber, we can have a polypropylene fibers, basalt fibers, and glass fibers. The weak performance of recycled aggregates can be neutralized by using fibers that effectively breach micro cracks and thus result in improved mechanical properties. Fibers due to their small microstructure size retard the origination and expansion of early micro cracks inside the concrete matrix. It improves splitting tensile strength, flexural strength, and ductility. As you may see, these are some of the fibers that we may use. We may use steel fiber, polypropylene fiber, basalt fiber, and also glass fiber. In our project, particularly which we are going to do with my PhD student, Mr. Wisama. We are going to use versatile fiber in the reinforcing the structure. Some of the challenges are here. First, high-tech equipment is required. Large-scale implementation, and sometimes we may obtain some undesired results, high-level expertise, and also some economic concerns. So, lastly, in this talk, I would like to introduce to you the objective, the overall objective of the project, PhD project. In our PhD project, which is going to complete in the next couple of years, we intend to develop an effective, practically viable, and eco-friendly treatment method for RAC. We also intend to determine the optimum content and proportions of pozzolana slurry to improve the weak interfacial transition zone in RAC via combined effect of pozzolana slurry and fiber reinforcing. We also wish to investigate synergy effect of modified RCA and fiber on the mechanical properties and durability of RAC. These are four of the outcomes. What do we expect at the end of the PhD project? We wish that we will be able to improve sustainability of construction industry, full-scale utilization of RCA for structural concrete applications. We wish to control the flow of C&D waste to landfill zones in Hong Kong. This is a very important issue in Hong Kong because in Hong Kong we are short of land. We also wish to save valuable land for waste disposal in Hong Kong. This is very important. And we also wish to create new business opportunities for the RCA manufacturers in Hong Kong. The research plans, this research plan is part of my research work, and I wish not to spend too much time on it. Some of the backgrounds, and we have 4 tasks in the PhD project: task 1, task 2, 3, 4. So actually 5 tasks, and the expected deliveries. I wish just to highlight that at the end of the day, we wish to obtain successful utilization of recycled aggregates for structural concrete. The flowchart, this one shows the flowchart of our work from literature review throughout the 5 tasks of the project, and at the end of the day, we wish to produce high-strength, sustainable, and eco-friendly fiber-reinforced RAC. Before I end, perhaps I just want to introduce to you a little bit of a fly ash in Hong Kong, as one of the speakers just now has already mentioned a lot, and also pozzolana reaction which is used in concrete due to its fueling and pozzolana reaction capabilities. Fly ash is very common here in Hong Kong, and also we have the silica fume, which one of the speakers just now has also introduced. And the method in our PhD project, there are 6 stages. First of all, the stage 1 is to produce NAC and the concrete crushing, cleaning, slurry preparation, slurry coating, and finally characterization. And after that, we wish to do some tests to show that the result can actually be obtained and the objective can be obtained. First, we wish to do two types of tests. One is the flexural capacity test, and which is will be the standard SDM standard will be followed. And the second one is the compression test, which we also follow the ASTM standard. Next, we will also do the split tensile test and also the impact loading test for the strength of the balsa fiber reinforced RAC. In fact, we have obtained some preliminary results in this work. By using the mixed proportion of the pozzolana slurry, and also a binder to water ratio of 1.2, our preliminary result has shown that water absorption can be reduced from 6.3% to 3.7%. And the work is going on, and we expect to achieve further improvement. This one is a conclusion of my work on my presentation today. The rapid increase of C&D waste, which originate from the booming in urbanization and demolition of old buildings, has steered the construction industry to the use of sustainable and resource-efficient concrete. Effective utilization of recycled concrete aggregates will help the construction sector in improving concrete sustainability, valorizing construction waste, and easing burden on landfill sites, along with fulfilling the demands of the present era. The use of high-tech equipment, large-scale implementation, undesired results, and higher costs are among the few limitations linked to the traditional aggregate treatment method. Pozzolana slurry coating is the most viable, effective, and environmentally friendly approach that, if combined with the fiber reinforcing technique, will greatly promote the application of recycled concrete in sustainable infrastructures. In the future, we will test the thermal performance and fire resistance of a proposed balsa fiber reinforced recycled concrete. The successful utilization of treatment, recycled aggregates, and balsa fiber will greatly improve the thermal endurance of concrete, and thus it can be applied in the sustainable infrastructure. To further highlight the usefulness of this method, we will perform detailed life cycle assessment. The successful outcome at laboratory scales, we will extend the applicability of a proposed method to the field. That is our ultimate aim. This shows some of the reference, including one paper that we have already submitted for possible publication, which is currently under review. Thank you very much. Hello? Hello, yes?
Yes, hello.
Yes, thank you. I will be happy
Prof.
to entertain any questions.
Yeah, so now thank you, Prof. Lee. Thank you very much with your great and very informative information presentation.
Thank you.
Okay, so now we open for Q&A. Any question from the participants?
Sir, I want to ask a question related to this ongoing project that is on basalt fibers, and you have used the basalt fiber in making a strong ITG bond between the aggregate as well as the inside the matrix. Sir, it is necessary to use the basalt fibers or the glass fiber. Instead, we can use nanomaterials or graphene fibers, as nanocracks can be healed up and it can improve the much more ITG as compared to the basalt fiber.
Sorry, if I may understand, are you saying that in addition to basalt fiber, well, is it possible to use any other fibers in for strengthening the structure? Are you saying that?
Yes, sir. Yes, sir. Because basalt, rather than using basalt fiber, I think nanomaterials, they are nano in scale, and obviously the crack rise from the nano scale to the upper scale or to the micro scale. So if we are going to use, if you and your colleagues just going to use nanomaterials rather than basalt fiber, it will be a good option to increase the to improve the ITG as well as the strength of the concrete.
Certainly. Basalt fiber is just one of the candidates. We opt to use basalt fiber because in Hong Kong we may we are able to obtain the supply of facade fiber quite easily, and it is also not very costly. It's also possible to use a nano technique to strengthen the structure, certainly. But as I think Professor Dr. Hamida, the first speaker, just mentioned earlier today, that nano materials not only requires higher technology, but also it is not cost effective. So in our project, we on one hand, we wish to strengthen and also to improve the characterization, also the properties of recycled aggregate concrete. On the other hand, we also wish to watch the cost. So we need to balance the 2 points. Of course, using facade fiber may not be the best, and we wish to move a step forward, and if we can find a better candidate which is available and cheap in Hong Kong, we are open for it. We are open-minded. We wish to try everything.
Thank you, sir. Yes, I would just like to appreciate it if you just find a good candidate instead of a salt fiber, you can use it. Thank you for that.
Thank you.
May I ask one question? I am Professor Amit from Technological University.
Yeah, please, Prof. Please.
Professor Lee, it's very wonderful lectures. We have enjoyed your lecture very well. So my question to you is, what is the durability aspects? If I use recycled aggregate in the concrete, how it is going to affect the durability of the concrete or life of the concrete?
Are we going to improve the durability of the concrete? This is one of our aims. By using facade fibers in the concrete, we intend to achieve certain improvement. It will be tested, and currently this work is going on. How much improvement at this moment? Unfortunately, I do not have data to show you. Okay. We hope to present, although to publish a paper in the future in this aspect.
Okay. Thank you very much. One more question. It is my eagerness to ask one more question to you. Is that what is the maximum grade of the concrete I can make with recycled aggregate? Is it any limitations of maximum grade of the concrete? What is the maximum strength I can achieve if I am using the recycled aggregate in concrete?
Okay. For this question, may I invite my student to answer to you?
Yeah.
Thank you for your question. Actually, the problem with recycled aggregate is that by using higher percentages, actually the strength of the aggregate is decreased.
Sorry.
Yeah.
So our aim is to utilize.
Sorry, not clear. Sorry, Prof. Lim.
Can you please speak louder, as we can't hear the voice?
Sorry, please.
Please louder.
Speak louder. Speak louder.
Speak near to your speaker.
Yes.
Okay. So actually, one of our aims is to utilize 100% replacement of recycled aggregates in the conventional normal strength concrete. And initially, we are targeting the grade 40 concrete. So we are hoping that by utilizing the pozzolana slurry in combination with the basalt fiber reinforcing, we will be able to achieve the grade 40 concrete that can be utilized in the structural members.
Okay, that's good. Thank you very much.
Okay, thank you.
Okay. Any more question for Prof. Amit and Prof. Lee?
Prof. Lee, your pozzolanic slurry, is it of a grade higher, slightly higher than the so-called the recycled aggregate?
Could you please ask your question again?
I'm questioning on the grade, or the strength of your pozzolanic slurry. Is it of a higher grade, slightly higher grade? Let's say you are comparing with the normal aggregate. but now you're using so-called recycled aggregate. So your coating on the recycled aggregate, is it going to be designed to be slightly higher strength in order to achieve that so-called better aggregate at the end?
Yeah, of course. It is one of the aim to achieve a higher grade strength of pozzolanic slurry. Additionally, the purpose of this pozzolanic slurry is to fill the micropores and by making suitable hydration products, and thus the properties of recycled aggregates will be enhanced.
Okay. The next question is the cost. Your cost of pozzolan in Hong Kong, is it a fraction of the cost of cement?
If you look, we are using in this pozzolana slurry two kind of waste. One is the fly ash and the other is the silica fume.
Yes.
As mentioned by the previous speakers, both of these are industrial byproducts. So we hope that if we replace it as a part of cement, it will be cost effective. And of course, towards the end, we will perform some life cycle assessment through which we will show that our proposed method has lesser cost and it's effective.
Yes, because I look at the cost aspect, silicon fume could be, say, $500 per ton, okay, as compared to the cost of, say, fly ash or GGBS. So my question is actually targeted on the lower cost materials such as fly ash and GGBS compared to cement. Because in Hong Kong, I'm not sure whether it has been monopolized by the cement manufacturer. Because other countries, it could be monopolized so that your composite cement or blended cement could be higher than the OPC. So in Hong Kong's case, I'm not very sure whether the price of the fly ash and GGBS is actually maybe 1/3 or 1/4 of the price of cement. That's my question.
Yeah, you're right. But actually, in Hong Kong, there are main two sources of fly ash. One is the Green Island cement, and the other is thermal power station. And initially, they have provided us with free fly ash. So, of course, currently it may have price greater than the cement, but in longer time, once the local plants are available, this proposed method will be of course cost effective.
I wish to supplement. In fact, we do not only look for local suppliers. We have actually have connection with the China suppliers, where we can actually obtain the not only cheap but also continuous and also relatively good quality. I'm not saying we cannot take for granted that the quality now in China is not reasonable. Actually, the quality is reasonably good and also continuous and cost effective. So
okay.
this is our objective. No, our advantage.
Yes, thank you.
So okay, thank you very much, Prof. Lee. Okay, so now we open for last question. Last question.
Yeah.
Yes. Okay.
Last question.
Any more question? Last question.
I've got a question here from Professor Amit.
Okay, yes, Mr. Zach. Dr. Zach, please. Yeah, Professor Amit.
I'm here.
Right. You were saying about reducing cement, right? You reduce a lot of cement, quite substantial, right? From 300 over kilo to 100 over kilo of cement per meter cube. All right. I know that you can still achieve the compressive strength required, but is there any problem with the PESA binder? Do you have sufficient binder, or will the concrete be kind of very fragile? It will break up easily and things like that due to continuous loading.
See, we have checked it.
Problem?
Yeah. When you are going, see, in the first section, we have discussed that what we can do maximum as per the codal provisions. And in the second sections, I have shown you what we have achieved. There we have replaced about 50% of the flyers, and the strength and durability, both part is very good. And in fact, it is there giving for making the self-compacting concrete, it is getting giving less load to the concrete pump also, because it is very smooth. And if you see the structure finishing, that is also very good. So there is no problem as far as the compressive strength is concerned, as far as the durability aspect is concerned. And as you are saying that during the earthquake or something, you are asking repeated load. What you are asking? What is the next part of your question?
Okay. So I mean, basically, there are certain codes, right? International codes where you need a minimum cement content. All right. For example, waterproofing structure, you need like minimum of 325 kilo of OPC.
No, I'll just stop you here. See, that we have to understand. When we refer our code or any international code, they don't talk about the cement content. They talk about the cementitious content. I have projected one slide. They talk about the cementitious content, and cementitious content is what? What is the ordinary Portland cement you are using, plus whatever is the supplementary materials you are adding it to it. That if you add up, that should be the minimum cementitious content. So, as I explained you, the minimum cementitious content for my M35 grade of the concrete, as per the IS code, is 340 kg per cubic meter. So out of this 340 kg, some part you can put OPS, OPC, and some part you can add the supplementary cementitious materials. As far as the IS code is concerned, they say that if it is a self-compacting concrete, the supplementary materials you can add up to 50% of the total requirement. So if it is 340 kg, then 50% of that is 170 kg. So 170 kg is cement plus 170 kg the supplementary materials like fly ash you can add. So that is the things. And we have checked it. It is going to not only going to control the strength, durability, it is going to control the temperature also. Previous to me, some speaker was talking and he was telling that the core temperature of the concrete should not increase by 70 degrees centigrade. So we have in one project, one challenge was there where we have the raft of about 3 meter thickness, and that raft was of M60 grade of the concrete. Very few times you might have listened about that M60 grade of the concrete in the raft, because it was a composite construction. And our challenge was to reduce the temperature of the concrete, and we have reduced it by using 50% of the fly ash and cold water and all. So this fly ash is not only giving you better strength and durability, but it's going to control the temperature difference and all. So in a region like India, where the temperature is very high, it's very useful.
Okay, I'm not disputing what you have just mentioned, but based on my experience, all right, practical experience. For example, right, let's say I do a concrete road, where the concrete supply, we do the test cube, everything. Let's say we meet the 40 MPa that is required, but we can see that the road starts to crack up, and then if there's any kind of a pothole, it start to spoil, start to spread like a cancer, right? But from my knowledge, if I use a OPC, 100% OPC, doing the same concrete mix, all right, without any blended cement in there, I find that this concrete is definitely much more stronger. It's not as fragile, you see, it doesn't break as easily, right? It's the same as if we need to break a concrete, we have to demolish the road. We find that if we have to demolish an OPC concrete road, we find it's much more difficult to break than compare with a concrete road that is made with blended cement. That is.
Yeah, I'm telling you. My answer to this question is what? Have you completed your question? Shall I reply?
Sorry, yeah, go ahead.
Yeah. My reply to this question is that during my presentation also I said, see, the way concrete we are using it, is totally decide what will be the performance at your site. Actually, proper good mix design supplemented with good quality control at your site. That mix design is not sufficient. I tell you, we have done the projects. I have shown you the projects where to the owner of the project, somebody said that, see, you are using very low cement. So maybe the QA strengths are, you are getting paused. And maybe that the real concrete, whatever you are having, that may not be having the same strength. So that project, the owner has decided to go for every month core test. They used to take concrete core every month because 3 story they used to do in 1 month. So after every 3 story, they used to go for the core strength, and everywhere the core strength was good, and it is as performing as it was performing for the ordinary Portland cements. And I tell you, the hard and softness in cutting is totally while you are using it, how you are doing it. And moreover, I tell you, this type of concepts are mainly there for the building projects and mostly for the building projects, because in the highway projects, the problem was what if you are using more flyers, the flyers is having the tendency to go up, because in the matrix of the total concrete, you will see the flyers is having the lowest specific gravity. So what it will do, it will try to go up in the matrix. And when your traffic movements will be there, then there will be chances of wearing and tearing. So that's why in the highway projects, this much cement content, fly cement content is not allowed. In India also, we are doing only 20%. But this is allowed when your structure is not subjected to the wearing and tearing. So like building projects and all, we are using it.
Okay.
Our housing projects.
Thank you for your explanation. Okay, then.
Professor Amit, you are making your own admixture, your own chemical admixtures, PCE?
No, we are not making our own chemical admixtures, but we have some idea about the admixtures, and with the reputed organizations, we tell them to prepare tailor-made. For my projects, I will guide them that what performance I required, and they used to prepare it. We check their performance, and when the performance is okay, then we start using it at the site. It is not that we are making the chemical admixtures. We get the chemical admixtures from the vendors.
Okay.
And that is tailor-made for us.
Are the chemical admixture made in India?
Yeah. So many.
Okay.
So many
are the chemical admixture PCE?
Yeah, they are making PCE also. Now this in India, since last 10 years, we are widely using PCE-based admixtures. Otherwise, before 10 years, it was the SNF-based admixtures or SNM-based admixtures. But mostly, at low-grade concrete, they are using SNF, sulfonated methyl formaldehyde admixtures. But mostly, like in self-compacting concrete and high-grade concrete, we are using PCE-based admixtures, that is polycarboxyl ether-based admixtures.
Okay, thank you.
Anything else? You are not audible. You are not audible.
Okay, sorry. Okay, thanks to Professor Amit with your response, very good response. Okay, I think that's all for our session today. Before that, I want to inform to all participants that please fill the Google form as attached in our chat column for your attendance and also certificate. Okay, all the materials will be emailed through your email address. Okay, inshallah. And then please don't forget, we will organize our second series webinar in September. Okay, and please don't forget to join us again. Okay, and we will invite another speakers from other countries. Okay, so thank you to the all speakers with your sharing session today, with your information, very informative presentation today, and also thanks to the all participants because joined us today. Okay, thank you very much.
Thank you everybody.
Thank you.
Thank you. Bye.
Thank you.
Thank you.
Bye.
Bye.
Thank you.
Good.
Terima kasih. Pak Haziman, Pak Isradi, terima kasih.
Terima kasih Pak Ihsan. Pak Ihsan, terima kasih banyak-banyak. Pak Isradi.
Terima kasih Pak Haziman. Terima kasih. Thank you Pak Haziman.
Pak Nawir, ya terima kasih kerana join.
Ya, thank you.
Prof. Zack, thank you very much. Prof. Hamida, Prof. Ari.
Right.
Welcome, most welcome.
Yeah, you are welcome.
Thank
Okay.
you, Dr. Haziman. Thank you very much.
Thank you very much. Yeah, thank you very much, Prof.
Yeah. Thank you for inviting me, for giving this opportunity. I think good opportunity for me. Okay,
Thank you,
everything
Prof.
goes well, I think.
Yeah, alhamdulillah, Prof. Thank you, Prof.
Everything
Thank
goes
you.
smoothly.
Yeah.
Okay.
Thank you, Dr. Haziman,
See you
for
in the
inviting me
Bye.
to attend this conference.
Thank you very much, Prof.
Thank you.
Okay.
Prof. Haziman, saya close ya. Saya ini.
Ya. Okey, boleh close. Nanti ada yang mau isi apa? Mau isi
form nanti saya share di YouTube.
Okey, siap. Okey, so saya rasa itu saja. Terima kasih Pak Ihsan. Nanti kita bisa ketemu lagi.
Ya, insya Allah pasti. Ayo, terima kasih Pak Isradi.
Okey,
Jumpa lagi.
terima kasih semua. Pak Nawir, terima kasih. Pak Nawir sudah keluar ya.
Nawir, terima kasih.
Terima kasih. Mana Pak Rektor? Pak Rektor Narotama kok enggak?
Sibuk dia cari uang.
Nanti Pak Nawir 22 Agustus ya, insyaallah.
Iya, 22 saya tunggu Pak Haziman. Siap. Nanti ada tim yang menghubungi Pak Haziman. Siap.
Ya, sudah ada.
Sudah ada. Oke.
Ya.
Thank you. Ya.
Okey, terima kasih. Nanti bisa ada second session untuk webinar CSM ini.
Oke, saya tunggu infonya.
Okey. Okey Pak Ihsan bisa.
Oke, saya live ya.
Okey.
Terima kasih.
Terima kasih Pak.